Okay, so we're looking at some material here from Unit 7-8, and this is Box A, the vector equation of a plane. And a good place to start is to sort of remind ourselves what the vector equation of a line looked like. So it had this form here, where we had some vector r, which we could also represent as a vector xy. And for a line, this was equal to, we had x naught, y naught, plus t, and then AB. And r, or xy, was the, we'll call it the position vector for any point on the line. Okay? So no matter what point we were looking for on the line, we could represent that point by using a position vector from the origin to that particular point on the line. And the way we could get that vector, the vector for any point on the line, was we had x naught, y naught, which was some point on the line. AB was our direction vector, which sort of told us what direction this line was pointing in. And by multiplying this direction vector by this parameter t, we could sort of move back and forth along this line. So we had some starting point on the line, x naught, y naught, a direction vector AB that told us sort of which direction the line pointed, and by changing the value of the parameter t, we could go further along the line or back in the other direction. And t could take on sort of any real value to get us to any one of these infinite points that was on the line. The vector equation of a plane, we're going to see, is very, very similar. So we can represent it almost exactly the same way. We've got r, again, which is the position vector of any point that is on our plane this time. We can represent that position vector as the vector x, y, z. Okay? Now we're working in 3 dimensions here because planes, well, you can have a plane in 2 dimensions, but you can only have one plane in 2 dimensions. So if we're looking at a bunch of different planes, obviously we're working in 3 dimensions here. And oh no, sorry, that's going to be equal. Sorry. So this is going to be equal to, again, we're going to have some point that we know is on the plane. We'll represent it by x naught, y naught, z naught, plus, and the big difference between the line and the plane is that where we had one parameter and one direction vector for our line, we're going to have 2 parameters and 2 direction vectors for our plane. So I'm going to use s and t here as our 2 parameters. And to represent our direction vectors, I'm going to use a1, b1, c1 with commas here, and a2, b2, c2 commas. Okay. So we've got 2 direction vectors. Two parameters s and t, which can both take on any real value. We've got a point that is in the plane, and r, or x, y, z, is, we'll just say, the position vector to any point. Position vector to any point. And okay, which is given by these 2 guys here. Now, let's give us a little bit more space here. when we're talking about these two direction vectors, both of these direction vectors have to lie in the plane. So two direction vectors in the plane, and these two direction vectors have to be linearly independent of each other. Now, once we have the vector equation of a plane, getting to the parametric equation is pretty much the same as what we did to get the parametric equation of the line. For a line, we just broke it up into our x and our y components, or if we were in 3 dimensions, our x, y, and our z components. Same thing here. So we're going to have our x is going to be x naught plus a1 times s plus a2 times t. So now our parametric equations are going to have a constant, in this case x naught, and two parameters, s and t, that factor into them. So we can do the same thing for y and z here. Y naught plus b1s plus b2t, and for z, we'll have z naught plus c1s plus c2 times t. It gives us our parametric equation. Okay? So completely analogous here. So I got a picture here that should help us try to visualize what this thing is looking at. The gray rectangle here is the plane that we're trying to represent. And if we want to come up with the vector equation of any of this plane, we want to be able to represent the vector from the origin to any individual point here. So our individual point here is x. So that is our x, y, z. Okay, has coordinates x, y, z. This vector down here is what we're calling vector r, or vector x here. To get to any point x in this plane from the origin, first we want to go to a point that we know is in the plane. So that's point P, or in our terminology, that was x naught, y naught, z naught. So that gives us the vector from the origin to the plane. So we've gotten into this plane here. Now once we're in the plane, we want to be able to go from that point P, which is like our starting point, to any other point that is in this plane. Now, when we're working with a line, and we wanted to go from the starting point to any other point in the line, we just had to go back and forth along the line. Now we have to be able to move in 2 dimensions in our plane. So what we want to be able to get is, from our starting point P, we want to kind of be able to get a vector from that starting point to any given point in this line. But if what we choose are 2 vectors that are in the plane, we can represent this vector from the starting point to any other point in terms of a linear combination of those 2 vectors. Okay? So that's why we need that second direction vector, because we're not just going back and forth on a line, now we're going in 2 directions in a plane. So we need those 2 direction vectors there. So the point, so we go first into the plane, and then these 2 direction vectors move us sort of around in the plane so we can get to any sort of point that we want. Okay? So let's take a look at, typical question that you might see here. Find the vector and parametric equations of the plane that contains the following 3 points. And they give us points A, B, and C. And we want to come up with the vector equation. So what we need for our vector equation are we need 2 things. So vector equation, we need a point in the plane, and we need 2 direction vectors. Okay, which are linearly independent. So the point in the plane is the easy part here. where do we get a point that is in this plane? Yeah, we're given 3 of them. So let's just use A here, 4, negative 2, 5. And we could have used B, we could have used C as well. Now we want our 2 direction vectors, which again, they have to be vectors that are in the plane. Well, we can get our direction vectors just by going from in between any of these points that we're given. So for instance, one of our direction vectors, I'll call this D1, we could just use the vector AB. Okay? And to find the vector AB, we're going to take the endpoint, subtract the starting point. So we get 3, negative 3, 1, minus 4, negative 2, 5. Negative 1, negative 1, negative 4. And just for your information, when the textbooks use a vector like this, what they like doing is changing it into something like this. Okay? Essentially getting rid of reducing the number of minus signs they have. So this is just a vector that is anti-parallel to the one that we found there. You don't have to do this step, but just so when you're checking your answers in the textbook, this is how you can get the same answer that they get. Another direction vector, well, we can just make sure we're going between 2 different points here. So we could do the vector AC, could be our other direction vector. We'll do 5, 2, 8 minus 4, negative 2, 5. Which gets us 1, 4, and 3 as our second direction vector. And then let's just put this together into the vector equation of a plane. So our point on the line is 4, negative 2, 5. We'll have one parameter S times one of our direction vectors, so 1, 1, 4, plus our second parameter, we'll use T times our second direction vector, 1, 1, 4, 3. Let's just try that again. T times 1, 4, 3. And that gives us the vector equation of the plane. And just like when we were working with lines, once we have the vector equation, it's pretty straightforward to go to the parametric equation. We just separate out our x, y, and z components. So for our x's, we're going to have 4 plus s plus t. For our y's, we're going to have negative 2, again, plus 1s, or just plus s, plus 4t. And z, we're going to have 5 plus 4s plus 3t. So those together give us our parametric equations. So, vector equation, parametric equations. Very, very similar to what we were doing with lines.
So, for our direction vector, do we have to relate to our first point, like A?
We could have used B or C there as well.
Like do BC?
Yep, yep. As long as you end up with, yeah, BC could have been one of our direction vectors. You could have done CB, done the opposite of it. As long as you're choosing a vector between 2 of those points, and you're good. Okay? All right. And that brings us to the end of A, sorry.